Here's another problem I've done. Again, the free body diagram. I draw this loop, go through the reactions there. So we have this 800 Newton per meter distributed load. I want you to get into the habit of actually drawing the distributed load in a free body diagram at first, and then converting it to a resultant load. And this will become important later in chapter 7. Okay, there's a roller at A, the ground is horizontal, so the reaction perpendicular to the ground is in the Y direction, and there's a pin at B, which means you have the X and Y reaction. So here's the real free body diagram. You can't really solve that until you replace the distributed load, that 800 newtons per meter, into a point load. The area of a rectangle is the base, and this is a 345, so it's 5 meters long, times the height, 800 newton meters, so newtons per meter. So 800 times 5 is 4,000 newtons. I didn't want to write 4,000, so I just wrote 4 kilonewtons. And the centroid, of course, of a rectangle is at the middle. And again, the length of the hypotenuse was 5 meters, so the middle of the rectangle is at 2.5 meters. Here's the free body diagram that you can use to solve for the reactions. And once you get that picture, it's easy to solve. The one thing is that you need to take that 4 kilonewtons and break it up into X and Y components. It's a 3, 4, 5 triangle with the vertical part being the 4 and the horizontal part being the 3. So taking 4/5 of 4, which is 0.8 times 4, I got 3.2 kilonewtons, and 0.6 times 4 is 2.4 kilonewtons in the X. Okay, we're ready to start. I noticed when I looked at it, there's 2 unknowns at B, so I took moments about B. That will let me solve immediately for the reaction at A. So taking moments about B, I'm taking counterclockwise as positive. RAY, its perpendicular distance here is 3 meters if you look carefully at the picture. And that 4 kilonewtons, its perpendicular distance from B is the 2.5. And solving for that, you get 3 1/3 kilonewtons, 3,333 newtons going up. It's actually 10/3. Okay, then once we have RAY, we can get the other Y reaction, RBY, by taking some forces in the Y direction. So here's RAY going up 3.33 kilonewtons. The Y component of that 4 was 3.2 kilonewtons. We did that earlier, going down, plus RBY equals 0. So in this case, RBY is negative 0.13 kilonewtons, means it's going down. That's kind of strange to think about. Why is that going down? That doesn't seem right, but I'll double check that later to make sure it's correct. Okay, then we sum forces in the X direction. You have the X component of that 4 kilonewtons is 2.4 kilonewtons to the left, and so that means RBX is going to the right at 2.4 kilonewtons. Well, I'm a little worried about this negative reaction here. That doesn't seem right to me, that RBY could be going down. So I checked it. I did moments about C, checked that it equals to 0. So we have the RAY 3.33 kilonewtons going up. So it's going clockwise around C, so it's negative. Its perpendicular distance was 1 meter. Then you had RBX 2.4 kilonewtons, and its perpendicular distance was 1.5 meters if you look at the 3, 4, 5 triangle. And then finally we have this RBY going down, so going clockwise around there, minus 0.13, and its perpendicular distance from the middle point C was 2. And it sure enough added up to 0 except for round off. And what's happening is the horizontal component of RBX is so big, it's making a big counterclockwise moment around C, that RBY actually has to be pointing down. So this is correct.